Hello everyone, this is a video lecture for Calculus 2, section 8.2, Surfaces of Revolution. So, last time we were talking about arc length, and now what we're going to be taking is that arc length and we're going to revolve it around an axis. So, for an example, this is a pretty easy example. Let's say I have some kind of curve here, and I, on the last section, was going to find the arc length right here. Yeah, from one point to another, this and that. Well, let's say I'm now revolving around this axis. And so what I've created is this cup, I guess you can say. It would be a cup. Something kind of like that. Notice that this is a little different than our disc and shell method because this is hollow. We were last time trying to find volume. This time we're trying to find surface area. Now, that's an SA, by the way, surface area. I personally like using SA, but, you know, as in mathematics here, we're in Calculus 2, S times A equals whatever? No. So a lot of times what we do is use a single letter nowadays, and so it'll just be a capital S. So capital S, which kind of looks like an integral symbol, huh? Just a thought, is going to be equal to 2 pi integral of f of x. No. I'll explain that. It's yes, but no. R of x square root of 1 plus f prime of x all squared dx. Okay, this R of x. I had mistakenly put f of x. And, well, it was just a mistake. But often, often R of x does equal f of x. Very often. Not always. Sometimes it's equal to just a plain old x. It kind of just depends on the problem. I have little notes about exactly where and when, but what r really is supposed to be, r is the distance from f to the axis. So the distance from your f of x to the axis that it's talking about, the revolving around. And so often what is going on is that this distance is itself f of x. Just for an example, let's say we had this guy again. I'm wanting that distance here. That's my r of x, I guess you can say. Well, it just so happens to be that this distance here is f of x. It's your height. It's your y value. It's the same thing. So that's why this sometimes, a lot of times, is just simply f of x itself. But what if we're revolving around the y-axis? What's the distance here to there? That would be my r now, right? Well, in that case, it's actually your x value. That would be your x value. So you would just say this whole thing here is just x. We'll see that in one problem, I believe. At least one. But most of the time, it's just f of x. Okay. Does the 2 pi look familiar to you? Yep. Does this kind of style here look pretty familiar? What about x times f of x? Does that sound kind of familiar? Yep. You know what's going on here? Is that this, actually, I kind of flipped it on you here just to be more proper. This is your f of x, and this is your x. This is shell method. This is like a shell method kind of thing. And how did I, here, I know I'm doing too much concepts. I know. Just fast forward or whatever. Why did I put this as a single x? Why is that important? Notice that I got the square root of the square of the derivative. And so my derivative, and I'm going to integrate it, turns into a regular old x. Just a thought there. I don't know. Don't take it too seriously. Okay. So let's start actually doing some problems here. 28009. There you go. So I got y is equal to x cubed. I got my x is going from 0 to 3, and they want to revolve this around the x-axis. So what does this look like? What's going on, etc.? Well, that's x cubed, which looks like this. And we're going from 0 to 3. 1, 2, 3. Looks good enough. And I'm revolving around the x-axis, so it looks like this guy here. And so it ends up being kind of like a cone, a funnel. There you go. It's like a funnel. So again, what's the surface area? How much material is required to make a funnel? That kind of thing. And so let's go and find it. My surface area would be 2 pi integral 0 to 3 of my r of x, again, I already explained would be my f of x in this particular case, square root of 1 plus f prime of x all squared dx. Cool. And so we have my f of x, and I can find my derivative of this guy. That's, again, my f, so my f prime, or again, y prime, or whatever, 3x squared. I should be able to put all that stuff in just as you see it. So I got my x cubed, square root of 1 plus 3x squared dx. And so on the inside here, we got a 9x to the 4th. We can use the u substitution for sure on this. And so then we got the 4 and the 9 makes a 36, sorry. Trying to remember all my multiplication tables. Dx. And so you can see that x cubed is going to go away here in a second. Du over 36 x cubed. And so now I got my 2 pi x cubed square root of 1 plus. Actually, this is all my u, so I could just say u. And then this is going to be a du over 36x cubed. These guys cancel one another. And so I get 1 pi over 18. See how the 36 and the 2 are going to make that 18 there. Integral of basically u to the 1/2 du. So I'm going to add 1 to the power and divide by the new power. From 0 to 3. Well, that 2 up here will cancel with this, make a 9. 9 and 3 makes a 27. And so I basically get pi over 27 of my 1 plus 9x to the 4th. That was my u. Now to the 3/2 from 0 to 3. Oh, I messed up here. This is x equals. I want to be proper. X equals x equals. Okay, now we're better. Plug in the 3, plug in the 0, because you actually get a value whenever you plug in 0 this time. And I get, I'm just going to go ahead and give it to you right now, it's pi over 27, integral of 730 to the 3/2 minus 1. So there you go, in its completeness. Next problem, 82012. I now have y is equal to the square root of 1 plus e to the x. Going from 0 to 3. I'm going to revolve around the x-axis. They want the surface of revolution, surface area, all that kind of stuff. So again, take the derivative of this. Pretty easy. That 1/2 is going to come to the front. Now this to the negative 1/2. Chain rule says that we have an e to the x attached to it here. And so then my surface area is now going to be the 2 pi integral of my original times the square root of 1 plus my derivative squared dx. Whew. Does that look crazy or what? Yeah, it does. Distribute your square to each of these terms here. And things are going to cancel here in just a second, but it takes a little bit of build up here. My square now makes a 1/4 e to the 2x, squaring it. And the square root and the square actually cancel one another, making this guy here in its original. What I'm going to do actually is a common denominator for all this stuff. And I know that seems kind of weird. Let me just verify here that I have one there. Yep. Yep. I think so. Give me a second. Hold on. I'm looking at my notes and I'm making sure that I am going to do this right. Why do I have it a negative half? Ah, I did mess up. I did. See it? See right here? Negative half. So this should be a negative 1. Now that makes more sense. I said common denominator. I'm like, I don't even have a fraction. What am I doing? So that's okay. It happens. 1/4 e to the positive 2x. And this guy right here is my denominator. See that? So I want a common denominator. That means that this guy over here is going to get that same format. I also want to make the 4 included with these guys. Um, Not that it's particularly important, but I think it'd be easier in the end. And so this 1 right here actually changes to be a 4, 1 plus EX, 4, 1 plus EX. And then over on this side, I've got E2X over the 4, 1 plus E to the X. Just like that. DX, I guess, sorry. So I had that common denominator because I want to combine my numerators together. Never said it was going to be an easy problem. So I've got now 4 plus 4e to the x plus e to the 2x all divided by 4, 1 plus e to the x, and then dx. All right, pause for a second. There's actually a major cancellation here at this point. It's right here. So the square root extends to the numerator, the 4, this guy, and so this guy's technically square root, and he's in denominator. This guy is square root, and he's in the numerator, and they cancel. Another one is that the square root applies to everything, including this 4. Well, this 4 inside the square root is a 2 on the outside of the square root. So these guys right here actually cancel. And what I get is pi integral of the square root of 4 plus 4e to the x plus e to the 2x dx. And although it doesn't look much better, it honestly is far, far better than what you think. Let's just say that I had instead a y squared plus 4y plus 4. Could you factor that? Well, yeah, it's 2 and 2, isn't it? And so what's going on, that was just like a demo of what's going on here. I actually have e to the x plus 2 squared. And what happens is that the square and the square root cancel one another, leaving e to the x plus 2, and then dx. I now add, oh, well, I guess you can add 1 to the power, divide by new power there. But integral of e to the x is simply just e to the x. So that one's not going to change much. The 2 is going to get an x next to him. He still has that pi. Both of them get the pi. So 2 pi x, I guess. And if you go back, it's 0 to 3. So I'm going to go ahead and put those guys in right like that. And so I get a weird answer, by the way. I get pi e to the 3 plus... Oh, hold on. Pi e to the 3 plus 2 pi times 3. And then when I do a 0, I get e to the 0, and then I guess minus 0 again here. So that doesn't matter. E to the 0 is a 1, but you got to retain the pi. And so my answer actually ended up being a pi e cubed plus 6 pi, 5 pi. What do I have a 5? Oh, right, because there's a 1 right there. Yes, pause for a second here. There's a 1 right there. What I have right here when I factor out the pi is that I have a 6, and then I have this 1 right here is a 1, and so I end up now with a 5. Okay, that's how I got the 5. That's why I have notes. It helps both of us. 82015. I've got x is equal to 1/3 y squared plus 2, and then to the 3/2. I'm going from 1 to 3, and then it says the x-axis. This is one of those classic problems that we had just seen earlier. This is kind of like that cup problem. So we just did something just like this. My notes, I have a full page devoted to converting this thing over to a y value so I can at least look at what it looks like. That's one thing. But secondly, to go and start integrating this thing. Because my thoughts were that I have my y is right here. And so then I need my y value, integral, I'm sorry, hold on. It's integral y, square root of 1 plus y prime squared, that kind of thing. And that is possible, but this is way too much. And so I'm just going to go ahead and skip all that junk and go right to what we need to do. So my integral, again, is going to be that 2 pi integral r of x, square root of 1 plus I don't know, f of x prime squared dx. Okay, that's good enough. And I was mentioning how r of x changes depending on what's going on here. Well, what if instead of saying x, 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 what if things were in terms of the y's, right? So this is my f, essentially. Okay, I'm going this way with my distances. Okay, so instead of going up and down like, what's my height? No, I'm going side to side. And that's why it looks funny to begin with. Also, they give you limits with the y's, so it kind of like, it helps us going in this direction, by the way. And so like I had mentioned way earlier in this section here, that distance to the axis, maybe I did the wrong axis. Regardless, no. Yeah, it's cool. No, yeah, it's not this distance here to the axis. That's my normal distance, x, right? But my distance to the axis is still this guy. Well, that's my y value, right? My height. Well, so what I get to do, and this is just a funny problem here, you actually just put a y right there. Because all of this is going to be my derivative with y's. So like right here, let's take a derivative of this thing right quick with some y's. So the 3/2 comes down to the front. The 3 and the 3 cancel, leaving a 1/2 in the front. I got y squared plus 2, and now that's to the 1/2 power. And then I take the derivative of the inside to get a 2y. The 2.5 cancel, makes a y on the outside. And then I got my y squared plus 2, and then that's a square root, technically, and then that's all squared dy. So notice what I did here. You don't have to put the function itself, because what you're doing is you're putting that height, which is just y. And so you don't actually have to put something complicated. It's kind of weird, but it works in this case. Distribute your square. And so what you get here now is y squared, and then y squared plus 2, like this. Okay, these cancel one another. You could distribute this as well. Y to the 4 plus 2y squared plus 1. I could factor that. So I got a y squared plus 1 all squared. Square root and square cancel one another. They do this stuff on purpose, by the way. It makes it easier on us, and that's a good thing. Distribute your y. So we got y cubed plus y dy. And again, we were going from 1 to 3. And so I got y, I'm going to put that 2 pi in the front here still. Got y to the 4th over 4. And then I got y squared over 2 from 1 to 3. And so I distribute my 3, I distribute my 1. Flip the page. And blah, blah, blah. I get 48 pi out of that guy. How nice. Okay, cool. Next one. 82017. This here, I have a note here. It says almost the same as the last problem. So, well, there you go. There's my note for that one. Next one, 82020. I got y is equal to 1/4 x squared minus 1/2 ln x. And we're going from 2 to 4, and we're revolving it around the y-axis. Now that's a first right here. So just be a little bit careful as I keep going here. First off, my y prime, my derivative is going to be the 2 comes down. I got a half x. And then derivative of the ln is 1 over x. Do you see something? Do you see something? Have you seen that before? No, I haven't seen that before. No way. All right, sorry. I was going way elaborate, my S. S, surface area, whatever. 2 pi integral of 2 to 4. Notice because, again, that was the y-axis kind of stuff, what you actually end up having, I don't know what this looks like. There you go. We have my arc length here. My r is going to be from the axis of rotation, but then my original f of x was this guy here. What I'm getting at is this is my r, and so how do I represent it? You actually just represent it with x. It's just x. And so you can just put an x here, and that makes it much easier than trying to do it another way. 1/2 x minus 1 over 2x squared. Have you seen this before? Have you seen this before? Have you seen all this before? In the last section, there's a trick to it. Honestly, I have it all written out to do the trick again, but I'm going to say go back to the last section. It was just the last section for this trick, and it makes it 50 times faster to just say, well, that's now a plus sign. And then the square and the square root cancel one another. And then you can distribute your x. And so we get 1/2 x squared, and then plus just 1/2. The x is actually just canceled there. And I'm going from 2 to 4. Okay. Cool. So now I actually need to integrate. Put a 2 pi in the front here. And so add 1 to the power, divide by the new power, that kind of thing. So I got x cubed over 3 there. And here this guy just gets an x. We're going from 2 to 4. Distribute your, plug in your 4, plug in your 2. I got a big long thing of what that looks like. Blah, 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 calculator. It's 62 over 3 times pi. Now, how do I get that with my calculator? I just get a big decimal when I try all that. Well, again, I've said this before. Get rid of your pi and just do all this math and see what happens. And then at the very end, just put a pi in there. That's exactly what I do. I'm literally telling you that's exactly what I do with my calculator. And it works. This is the last problem. So here we go. 82034. So I've got my y is equal to e to the negative 3x. I got x is greater than or equal to 0. And they want to go around the x-axis here. This function looks something kind of like this here. We're going around the x-axis. And they want to go from 0 out to what? X greater than 0? Yeah, you're right. They actually want to go to infinity with this thing. They want this surface area. And so what's going on is it's kind of like a big, big upside-down funnel thing. But it's infinitely long. It'll keep going forever. And I hope that you're wondering, hey, is this even possible? And in some cases, it might not be. It is possible to get a definite single answer here, like a numeric answer. But in other cases, it's not. Okay? And that just depends on what the function is here. But all the same, though, we're just going to do the same formula, I guess you can say. I'm just going to go from 0 to infinity this time. E to the negative 3x. Again, that's my r of x, that distance. I need to take a derivative. So when I take a derivative of this, I bring the negative 3 down to the front. And again, I'm squaring that. dx. So when I distribute my square, kinda, I get a positive 9, e to the negative 6x. Apparently that's not what you should be doing, though. Pause for a second here. Let me just look right quick. Yeah, they don't want you to do that. I don't know. Let's just pause for a second. I'm going to do it a little bit differently than even my notes here. Notice that I got a negative squared, so I'll definitely end up with a positive regardless. But I'm going to put a little square there. What's 1 squared is still 1, right? It doesn't really change anything. And so what you're doing is you're developing a particular format here. And what I guess you could say, like, got down to is a u substitution. So I'm going to do u is equal to 3. That's Yeah, that's a 3x. Okay, you were cool. And then that's still a negative, isn't it? Let me just verify here. Still a negative. Yep, sorry. There's still a negative there. Okay, so my du, again, my derivative of this guy, 3 comes down. I got a negative 9e to the negative 3x dx. So my dx is equal to du divided by the negative 9e to the negative 3x. I'm going to use these two right here and plug them in. So 2 pi integral e to the negative 3x square root of 1 squared plus u squared. And then I got my du divided by negative 9e to the negative 3x. These guys cancel out right here. The 9 can come to the front. So negative 2 pi over 9 integral now of 1 squared plus u squared du. We saw this, I'm pretty sure, in the last section, because I just saw it a second ago. And what I did to accomplish this was I did a formula. I can't remember what that formula number is. Just verify, because I got a different number in the front. I got a 2/3, not a 2/9. No, I do. I got the 2/9. Okay, we're good. Because I did it differently than my notes. Use a formula on this guy right here. It's deceptively hard. It's actually a hard problem. And so what you get out of this is the 2 pi over 9, and then I've got some big stuff here. So here we go. The best I can show you is 1/2 3u. Let me verify I'm doing this right. My u is different. See, I have a v substitution, kind of weird here, actually. So I think I'm just going to piece the puzzle together here. Hopefully I get it right there. I'll give you the answer, and you'll at least be able to decode that a little bit there. My u squared plus 1 plus ln of u plus, and then I got my u squared plus 1. Something like that from 0 to infinity. Something like that. And so you plug in your e to the x stuff. Oh, see? It's x equals 0. X equals infinity, right? Yeah. The 1/2 you can actually make an 18. Makes it a little bit more convenient there. And so I got my e to the negative 3x. E to the negative 6x plus 1. There's a 3 in there, isn't there? There's like a 9. Because that was 3, square the whole thing, get a 9. Yep, okay. Just watch out. Watch out. There's all kind of little knick-knacky things going on here. There's a 3 there. It's a 9e to the negative 6x plus the 1. Close that off. From, now again, x. It's already implied now, 0 to infinity. Okay. So then when you plug in the infinity, or whatever, do the limit, I don't know, whatever you want to call it. Let me see. I think you just cancel a lot of stuff. Yeah. Let's plug in this infinity. I'm going to use a different color to show and demonstrate. So this infinity here, when I plug it into this guy right here, you end up with a 0. E to the negative infinity is definitely 0. So this whole thing right here just goes away. Same thing with this here. You're going to get a 0 here. And you're going to get a 0 here. So you got square root of 1, and ln of 1 is also a 0. So all that goes away. And then, so it's 0 minus a negative 2 pi over 18 times all this stuff here with 0 plugged in. So let's kind of see what would happen with the 0. Again, 2 negatives make a positive here in a minute. With the 0, if you have a 0 here, this makes a 1. When you have a 0 here, that'll make a 9 plus 1 in the end right there. When you plug in a 0 here, you get a 3. When you plug in a 0 here, you get the square root of 9 plus 1 yet again, so square root 10. And I believe it should just end up being then square root 10 plus ln of 3 plus the square root of 10. And I'm going to verify my notes right quick. I have a very small difference. There's actually a 3 right here. I should have put that 3 right there earlier. Every one of these has a 3 in the front. I don't know why I didn't put a 3 there. So that was my mistake. That was a typo. And so that actually the answer is a 3 there as well. That's what my notes say here. 2 negatives make a positive, and there you go. So my final answer, 1/9 pi of 3 square root 10 plus ln of 3 plus the square root of 10, close, close, and there you go, the end. It's approximately 3.94628, but I don't think they care about that. Okay, cool. I think that's it. Thank you very much. Have a great day.